Good morning. This is a tutorial that will be that is being offered as part of the ENGI2203 course to help support the um, lab sessions and to help better understand the embedded processor that we will be using during the project. Now, the specific objective of this tutorial is to actually introduce you to the embedded processor. This board that will be provided to you as part of ENGI2203 has been built for our students and will be used in this course as well as further courses that are taught in the ECD department. As you can see on this board, there's multiple chips, but at the heart of the system, you have the embedded processor over here. So this is an ATMEL ATMega 644A chip. It has several features that allow you to control actuators and to sense information. To help you use this chip, we've built in a development board, right? And so the headers that you see on this side of the board are actually simply extensions of the pins that you see on the ATMega. So you have the different ports are available, port A, B, C, D, as well as a voltage supply that's provided by the embedded processor. There are other additional pins that allow you to do various operations with the embedded processor. Another very important device that is on this chip is the oscillator. So there's a crystal oscillator. It is situated over here. Okay, and this little crystal oscillator is intended to operate approximately at 14.7 megahertz. It's a clock. So without this, you wouldn't be able to generate operations at a regular rate. This the clock over here allows you to run a sequence of operations on an embedded processor. Another important feature is the USB port. So this USB port allows you to connect to your computer, right? And we'll be able to not only download our programs, but we'll be able to communicate to our device using an RS-232 interface. To communicate to the embedded processor, there's an interface chip. So the little black chip that you see over here, this is an interface chip that allows you to do the communication. It simply converts and translates the different commands so that the embedded processor understands them. And in fact, to actually communicate to the chip, you have to make sure that there's two jumpers that are labeled as TXD and RXD. The jumpers have to be soldered. I don't think that this will be, perhaps this will be visible over here. Actually, I think it is visible. So you can see it here. You have two jumpers, and I've actually soldered two beads on top of the solder so that we have a connection between the two interfaces. I think those are the important features of the board. Oh, and another important feature is the power supply connection. Okay, so the embedded processor kit allows nominally a 9-volt voltage supply, but you can actually supply it with different values. So for example, I bought myself a little battery. It's a D-Link that I bought at Walmart, or yeah, Walmart. You can probably find one at the source also. So this one is a 7.5 volt. Actually this one's a 5 volt. I also have another one that's a 7.5 volt. So this is oh yeah, that's right. Sorry, I read too quickly. This is a 7.5 volt, 1 amp maximum rating battery supply. So you connected it into your board, and it will supply you with DC power. Now, to connect this battery to your embedded processor kit, we sell additional connectors so that you can actually plug it into the embedded processor. So I plug it over here. This is my DC supply, and I plug it into the wall. In my case, it's my power bar. Okay, excellent, excellent. So this is the embedded processor, but so one of the nice features of this embedded processor is that you can connect it easily to a breadboard, and that way it allows you to extend your circuits and build some circuits on your breadboard that will be able to interface with your embedded processor and do actual control of and sensing of different devices. So how do you connect this properly? Okay, so to be able to understand how to connect this properly, what you have to do is you have to understand the two pins that are over here. Okay, so there's two pins on the backboard, and they're labeled on the front side of the card. So there's one that's ground and there's one that's VCC, or it's your supply. There's one that's ground, there's one that's supply. Your supply voltage is the output of your battery. Okay, so how will I connect this? Well, normally on a breadboard you have two rails on each side. Okay, and one of them is going to be a ground and the other one is going to be a supply, right? So you got to make sure that the ground and the supply are properly labeled. So what I do over here is I make sure that my ground is in the blue. My ground must be in the blue, and my VCC must be in the red, and the rest of my headers will be connected to the horizontal lines. So you'll be easily able to do some circuits over here. So let me just put it in here. Okay, so I've put it in here like this. Okay, so you can see on the outside I have my red line, my green, my blue line over here, because this is my ground, right? You see, I've done it upside down. So we're going to do this again. My V plus is in the wrong one. I have to do it opposite. That's a mistake. Okay, so we're going to do this again. I'm going to flip it around. That's a good example of doing the thing the wrong way. So we're going to do it the right way this time. We're going to put our V plus in the red rail, the ground in the blue rail, and our header is going to be in the first column of the horizontal traces, right? So then once I'm properly aligned, I just punch it all in. Okay, so now what do I have? I have a supply rail, a ground rail, and then I can extend my headers and build some circuits around here. Oh, I'm sorry. Okay, so I'll do this again. This is my supply rail. This is my ground rail, and this is the header over here extends so that you can build circuits between these horizontal traces. Okay, so it's actually giving you a lot of flexibility. Okay, so I'll show it to you a little bit later, but this is what it looks like. Okay, so for the tutorial that we'll be presenting today, the objective is going to be able to control an LED and make it blink using using our embedded processor. So you're going to have an LED and you're going to have a resistor. I'll just place these two components onto my board. The LED, the long end of the LED, is actually the cathode. So it's the long the long leg is the positive side of the LED. So I'm just going to connect it, and I'm going to connect the resistor right beside it down to ground. Okay, so there's a very important thing that you have to remember about the embedded processor is that so these headers are actually connecting into the GPIOs of the embedded processor, the general purpose input outputs of the embedded processor. So when you're reading them and when you're reading the signal, a voltage will be converted to a logic value, right? And that's important to understand. So If I put a 5 volt, so the embedded processor is nominally operating, the GPIOs are operating at 5 volt, even though we're supplying at the input of the voltage regulator. I'm supplying it with 7.5 volts. Here at the headers, I'm not supposed to give it more than 5. And if you give it more than 5, there's a good chance that you're going to fry your circuit. So make sure that all the signals that come into your headers never go above 5 volts. So a 5 volt is a logic 1 and a 0 volt is a logic 0. So how am I going to connect 5 volts into my circuit? Well, one of my header outputs is a 5 volt. So that's what I'm going to do. I'm going to extend that 5 volt. I connected it at the wrong place. I'm gonna do it. Okay, and I'm gonna connect it to the next rail. Okay, so this rail over here, this will be a plus 5 volt rail. Okay, I'm gonna make this one, the blue rail over here. That's another important thing, is I want to make this another ground rail. So I'm going to short all my grounds together. These become references. Okay, so this is my ground reference. Okay, so I've got everything connected on here. I've got all my components and I've got all my setup. So there's the hardware. Now that I have described the hardware, I hope I've given you enough of information to be able to understand it. The next thing to do is to actually introduce you to the software. Okay, so we're going to launch the software. Okay, so as I said before, so the next step now is to actually show how the software works. And since we're using an ATMEL microcontroller, what we're going to be doing is we're going to be using a software that's provided by ATMEL. The software that we're using is called ATMEL Studio. You can download it for free. It's available for free for all. So it's the current version that I have is ATMEL Studio 7.0. It might have they have regular updates, so making sure that their development kit is up to date. Having said that, the 7.0 is fine enough, and you may also be able to try with more advanced versions of it if they're available. Okay, so this is the basic look of your editor. And what we're going to do is we're actually going to create ourselves a new project. Okay, so when we create ourselves a new project, the first thing that we have to say is we're going to have to say which language we're going to be using and what type of project we're going to be running. And this is going to be an executable project that we're going to run, and we're going to be running an executable project that is going to be compiled as a C project, not a C++ project. We're going to give it a given name that we like. That is, I think it's very important in software to actually provide names that are relevant and that we'll be able to remember. So in this case, I'm going to call this intro, embedded processor intro. Embedded processor intro. Okay, and it's going to be located in this directory. It's important to remember what directory it's going to be located in, because it's we're going to be browsing for our executable in this directory. Okay, so let's just create this project. So there's a wizard behind the scenes. The wizard will configure the project for us. The first thing that we have to say is we have to provide the adequate device so that the proper libraries are loaded for the project. So in this case, we are using the ATMega 644A. Okay, so there's an AP and there is also a P. If you look very carefully on your black chip here, you should be able to see what is the version of it. In the past, that we've also offered the AP, I believe. So you have specs here on your chip, and you can also actually load the data sheet from here. This is always a good idea. It's always a very good idea to have your data sheet handy. Okay, so let's click OK, and then like I said, what's going to happen now is it's going to load some libraries, and it's going to create yourself a main function. By default, the main function is what gets loaded. So just to give you a very rough overview of what the main looks like, well, we first start by providing the header to the file, and this is a standard procedure. So in this case, they abbreviated my name to JF, but we're gonna make this a little bit more formal. It was this is the creation date. You know, this is your copyright information, so it's actually quite important. When I define functions, I like to separate them with headers. So I'll show you how to do that in a minute. And this is our main function, and this is where the program starts. So when your program starts, the first line of code that's going to be read is in the main. We have a while here. We have a while and we have a condition. The condition that is used in this case is that it's always respected. Okay, so since it's always respected, what's happening? Well, we're running an infinite. This is an infinite loop, right? We're never going to come out of this loop. The only way that we can come out of this loop is if we disconnect the embedded processor and we turn the power off, right? And then put the power back on. Well, the main is going to start running again. Okay, so these are subtleties that are important to understand when you're working with embedded processors. So as the comment mentions here, this is where we're going to be placing our code. And typically what you do is you start by putting initialization commands. Here I place, here I place initialization commands that I will only run once. Commands that I want to run once. And here in the while loop, I'm going to, here I put actions that I want to run periodically and continuously. Okay, I hope this makes sense. Okay, so in fact, so if you look at the lab manual, I provided you an exercise to run during the lab. And this exercise, I've given you in the instructions. I've given you the exercise I've given you is to be able to make an LED blink when a switch is set to high, right? So when a switch is enabled. So this is what we're going to do. And I'm cheating a little bit here. I'm going to use the code that I provided you online, and I'm going to copy it into this project. So I've got the code in a Word program, and I'm just simply going to copy it. I don't recommend that you do this. I think it's a much better idea for you to write it out on your own, so that you can actually understand. You get a much better education when you do things yourself. I don't know if that makes sense. Okay, so now I've just replaced my main file, and as you can see, I've also included a header here. In this main file, there are some variables that have appeared, and it's funny because this is certainly a syntax that you haven't seen before, because it's syntax that is used in embedded processors. So I don't think that most of you will have seen this type of syntax. So where does this variable define, you think? Where do you think this variable is defined? DDRD. Every variable that exists in program must be defined somewhere. So they're defined in the ATMega library somewhere in their files. So what we'll do is we'll go to the implementation. Okay, so there's a file that opens up, this file iomxx4.h. Okay, and in this file you have a bunch of variables that are defined there's a huge amount, and this actually defines all the registers that exist in your embedded processor. So it allows you to control your embedded processor uh, uh, more simply. It gives you a proper interface to your embedded processor. So for example, what does this variable stand for? It's my data direction register for port D. Okay, what am I saying now? What am I going to be doing with this variable? Well, I'm going to be saying, well, set the content of this data direction register D variable to be equal to this value. Okay, so what is this value? This is a syntax that you've probably, again, I'm introducing to you. What do these two arrows pointing to the left mean? It means I'm going to be putting a 1 in my data direction register, but I'm not going to be putting it at the lowest bit. I'm actually going to be advancing. I'm going to be pushing the bit to the to the left by a value of PD0. Okay, so why do I say PD0? That's where I'm going to actually be writing. Okay, so so as per the comment, what I'm doing over here is we're setting the data direction register at D0 so that it is in write mode. Okay, so this is a little bit too long. I'm probably beyond the 80. In software there's a convention that says, well, you should never go beyond 80 characters in a line, so it kind of matches with my header. Here, by the way, if you were to do this properly, you would say this function description. You would say function description. You would describe the function description. Well, what happened? What happened? What happened? That's not supposed to happen. Okay. Inputs. And outputs. Okay. In the case of a main, there's no inputs. There's no parameters. And output values. Output return values. Okay, so please describe them. So what's in this case? What do I return? It's an int. What am I returning in this case? What am I? Oh, actually, this is a compilation error. Or it's going to be a warning, but you should be returning something. In this case, I'm going to return a 0. I just return. When you return a 0 by convention, a 0 means that everything went well. Okay, so at the initialization stage, okay, so this is an initialization. Okay, initialization. I'm going to be setting the data direction register on port D0, on pin D0, so that is in write mode. We're going to write 0 to this port, and then we're going to loop forever. And then in this loop, what I'm going to do is I'm going to be checking pin D7. Okay, and again, this is another syntax that I'm going to teach you in lecture time. Okay, I'm not going to be going in extensively into what all this is, how this syntax is read, because it's going to, I'm going to go beyond the scope of the tutorial. And then I'm going to put on port D. I'm going to make this port D I'm going to put a 1. So what that means is I'm going to actually force port pin D0 to be equal to 1. And then I'm going to delay by 5,000. Okay, so what's this thing? It's a delay. I'm calling a function, right? You can recognize this. This is calling a function, and this is the parameter to the function. Now, function call is in red. Why is it in red? Because the function doesn't exist. So what will I do? Well, I need to create myself a function. But before I create the function, just what am I trying to do here? So if I've activated the switch on pin D7, what's going to happen is I'm going to toggle the output pin on D0. Okay, I'm going to be delaying every 5,000 milliseconds I'm going to be delaying this. Okay, so this is the function call is with a parameter in number of milliseconds. Okay, so let's actually create ourselves this function. How do we create ourselves this function? Okay, so I'm going to go and get it. Again, I've cheated, and I've already copied this from online. And I'm going to take all this stuff. Okay. And I am going to put it. I'm going to put it at the bottom. Okay. What happens if I put it at the bottom? Okay. You know what? Let's try to compile this. Okay. So this function is a function that delays by a specific number of milliseconds. Okay. We're going to be using the hardware configuration, particularly of the counters, to be able to generate a delay. Okay, so there's a few things that you need to know. The input oscillator is approximately 14.7. Actually, there's a much more precise number there in your instruction manual. You can have a look at it. It's 754. I don't remember, 45 or something. But please have a look at it. Make sure that you have the right value, because you want to be quite precise at the end of it all. Now, I define myself a variable I, and then I'm going to be looping this I until I reach the proper amount of delays. So the variable I here, which is not very descriptive, what it means is it's the current it's the number of milliseconds that have expired, right? So I'm going to be running this loop until I've reached 5,000 milliseconds in the case of that call that I've in the case of the example that I have here. So now you're going to set a bunch of different registers to configure the counter value. I was writing. So I don't want to go into the data sheet. I always recommend that you have the data sheet available, not too far. It is open in my case somewhere. I thought I had it open. If it's not open, we can simply open it here. It's on my desktop because it's my best friend. If you're looking for something like CS12, you can go look for CS12, and it's going to give you a nice table that explains to you by what I'm going to be pre-scaling that clock. So that's actually an important number. I've given you some comments to help you, to help guide you through understanding how this works. But generally speaking, every time we go into the loop, we're going to be delaying by 1 millisecond. So to do that, we're going to reset our settings of our counter, and then we're going to be comparing the number of counts at the output of the that are counted by the clock and until they reach a value of 14. Okay, and there's a division factor before that, but we're going to be counting until there's a value of 14 that's reached. And that value of 14 will allow you to have approximately a 1 millisecond delay. This is the procedure that we've had. When the counter reaches this value, the output compare flag is raised. So this over here is a while loop. Okay, so this while loop is waiting for the output compare flag to be raised. And when it is, we're going to advance and we're going to go to the next millisecond, and we're going to repeat this loop until 5,000 steps have been repeated of this. Okay, that makes sense? Good. So now we've got a program. Let's try to see if it compiles. I expect that it wouldn't compile personally. Sometimes you can be surprised, but we'll see. So you see it's compiling slowly. Okay, so now it says it can't find the function delay. Oh no, this is actually a warning. It's not even an error. I'm a little bit surprised. So why doesn't my implicit declaration of function delay? Why doesn't my main see the delay function? Can anybody give me the answer to that? Okay, so the reason is because we've put that delay function, we've put the function definition below the main. Okay, so in order for the main to be able to see the function delay has got to be declared beforehand. So what I'm simply going to do is I'm going to provide a signature for this function, and the signature is going to be provided up here. Okay, so just going to go like this, and it's just, that's my signature. Okay, so now we're going to try to rebuild this. Rebuild the solution. So right now what I'm doing is I'm actually compiling. Right, so we're going to see, oh, it succeeded. Great, we're happy about that. Happy face. Okay, that's usually how the software guys like to say. Okay, so we've got our happy face. The next step is to go and download this to our embedded processor. So let's do that. AVR USB prog. Okay, so this is a program that's been written by our technicians, and it's available on Dalhousie on the Brightspace. So normally, if everything went well with your hardware, you should have been able, this program will pop up without any errors. If you have problems with your jumpers, then we may have some problems. Okay, so before I go into describing the actual download procedure, I'm actually going to flip the view so that you can see the status of the embedded processor as I'm programming through it. So just give me a second here. Okay, so when I actually let me actually restart my software. I want to show you what the behavior of the embedded processor is as we restart the AVR USB prog. You'll see that there's lights that blink as we do so. There's a few things I want you to know. The jumpers, so there's red jumper over here is on reset, and the black jumper over here is on SS. Not sure what it means, but those are the settings that it has to be on for it to be able to operate properly. So once we've done that, then the next step is for us to go and load our just give me a second here. There's something that seems to be off here. Sometimes it does that. We're going to load our program into the flash memory. So over here, what do we call it? Embedded processor intro. Okay, so it's this one. Okay, so I go into debug. I'm looking for a hex file. So I'm looking for this hex file. So it's a hex. I'm assuming it stands for hexadecimal. So this is the output of the compiler, and the output of the compiler produces a set of binary commands that are going to be loaded into the flash. So it's going to be basically saying what are going to be sequentially the order of events that are going to happen in the embedded processor. So okay, so I've loaded the program. Once I've loaded the program, I will simply click on Program Flash, and then the program is written. Okay, now the one thing I haven't done yet is I haven't put my switches and my LED at the right place. So what did we say? We said if we look at our program, let's go back at our program. We said in the main, okay, pin D0 is used to plug into the LED. Okay, so we're going to do that. Let's plug D0 into the LED, or the other way around, I should say. So the LED goes into port D0, and it's a short circuit to ground. So I mean, I can draw you a little picture of the schematic here. So what am I doing? I'm doing something that looks like this. I'm gonna move this around here. So what I'm doing over here is I'm saying my um, my source, which is a microcontroller, okay, it's going to be producing 0 or 5 volts, okay. So that produces 5 volt or 0 over here, and it's going to be feeding into an LED like this and a resistor like this. Okay, so the resistor that I chose is a 1 kilo ohm resistor. The smaller the value of the resistor, the more light that's going to appear in the LED, because the LED intensity is defined by the amount of current that flows in here. Okay, so, okay, great. So I've done this. Everybody saw this little drawing? Yeah, okay. So let's move it back. So that's my circuit here. Okay, hey, it's not yet flashing. Uh-oh. That's okay. It's because I haven't finished wiring my circuit. I need a switch, right? So that was put into D0. You always have to make sure that you've aligned things properly. Okay, and then in D7, I'm going to put this in D7. Okay, okay, so this is on. I'm going to put it here. Okay, okay, good. So, is this supposed to be starting up again? Every 5 seconds, my light's supposed to go on. Is that right? It's not going on again. How come it's not going on? It's simple. It's because I haven't activated my switch. I'm going to activate my switch by putting it into the plus sign. Okay. One thing about the embedded processor is that those GPIOs are hooked onto pull-up resistors. Okay, so by default, if there's no connection into the into the headers, by default, the data gets pulled to 5 volts. It gets pulled to a positive value, right? A logic 1. So that's why even when I don't have this connected, the PD7 is currently a logic 1. Okay. Otherwise, if I put it back to 0, boom, everything turns off. Okay, we're done. We're done. There's subtleties also that you can notice. It's not automatic. How come? How come? Okay, so right now I've got it logic like this. Okay, I'm gonna unhook it at the beginning. Okay, so now I've unhooked it, but it's still red. Why is it still red? Well, I'll ask you to look at the code and try to answer this question for me. Okay, would there be a way for us to automatically put it back to off without us having to wait the extra time there? So those are the little things that you want to know, that you want to be able to understand. So I want to thank you for your attention, and I hope this was useful. If you have any questions, you can contact me at my email at jbousquet@dal.ca. Thank you very much for your attention again. Bye-bye.